All right, this is our third session about tension and inclined planes. It's more of a sort of an applied forces session. Forces are one of the most important topics. They cover the most in what we do in AP Physics 1, so it's really important to look at it. So we're going to look at a lot of different problems with tension and inclined planes. So for tension, here's our first one. Oh, and same thing as before. Pause before I go over a problem to do it, and then listen to the solution first. So please take that time. All right, number one. The system in the figure consists of a ball attached to a cord attached to a large wood block. If the system is allowed to free fall, what's the tension in the cord? So we want gravity to be in free fall. So let's look at this cord, and let's look at the free body diagram for the ball. We just look at the ball, and we can do the same thing with the weight. So the ball has force of gravity pulling down on it and possibly tension pulling up, and the ball is in free fall. One of the things that we should always do is that when we're in free fall, we should write down that the acceleration is equal to 10 meters per second squared down, or it's going to be the acceleration due to gravity. Whether you use 10 or 9.8, doesn't really matter, but we need to think about that every time we see free fall or projectile or balls thrown into the air. We need to always go with that being 10 meters per second. So for this picture, the acceleration is down because we're in free fall. We know the value for that's going to be 10 meters per second, or the value for that's going to be g. So the net force here is mass times acceleration. If we're going to get the net force, what's important is looking at how those forces relate to the acceleration. So if we look at the weight, since the weight is in the same direction as the acceleration, we want to make that positive. And if we look at the tension, it's opposite the acceleration, so we're going to make that. All right, so weight's positive, tension's negative. That tells me when we add up our forces, it's going to be mg minus t is equal to ma. So we'll plug in the numbers that we know. We don't know the masses, so we have mg is 10 meters per second squared down, minus t is equal to m times 10 meters per second squared down, because we're in free fall. If we look at that, this term and this term are the same. The only way that this mathematically works out is if the tension is equal to 0. Looking at this situation specifically, both objects are in free fall. Both of the objects are in free fall. Because of that, there will be no tension in between them. There's nothing that force can do to the acceleration in this case. They're not pulling on one another at all. Here's a different one. This time we're not in free fall. So let's look at number 2. All right, we have a 44.5 Newton weight hung from a scale. Scales indicate tension. And the scale is hung on a string, and the assembly is allowed to accelerate down at 4.9 meters per second squared. Now I want to know what the scale reads when that happens. So, if the acceleration were 0, the scale would read the weight of the object, 44.5 newtons. But it's accelerating down, so things get a little tricky. Because it's accelerating down and we want to find a force, this is a force problem, and our method for force problems is to first begin with a free body diagram. So we have our mass, we have tension up, we have weight down, and we're accelerating down. So looking at all this, the net force acting on this mass, the acceleration is down, so weight is positive, tension is negative. The net force then is going to be mg minus the tension, because they're in opposite directions, and we make the thing with the acceleration positive, is equal to mass times acceleration. Now I already know the weight because they're telling me it's a 44.5 Newton weight, minus the tension is equal to the mass times the acceleration. Now, that's not the mass, that's the weight. They're specifically telling us that that's a force. That force is 45 newtons. So I know in general the force of gravity is mg, and that's 44.5 newtons. So the mass is 44.5 newtons divided by 10 meters per second squared, giving me 4.45 newtons. Sorry, giving me 4.45 kilograms as the mass of my object. 44.5 newtons minus tension equals 4.45 kilograms times 4.9 meters per second squared. So if we solve for the tension, it's going to be 44.5 minus 4.45 times 4.9. That's going to be my tension. Plug all that in, and the tension comes out to be roughly 22.2 newtons. About 22 newtons. This is the basics of finding one force when we know the acceleration on an object. All right. With a man riding in an elevator and he's experiencing a normal force that is greater than his actual weight. So we want to know which of the following statements could be true if he's experiencing a force greater than his actual weight. So here's the man in the elevator. There's a normal force, there's the weight, and the normal force we're told is bigger than his actual weight. If that's the case, the man is going to be accelerating up. The unbalanced force in this situation is up. So there's an upward unbalanced force. And the man is going to be accelerating up. So that's the first part of this. The second part of this is actually deciding what upward acceleration is. So right away we can say constant speed is not acceleration, because every time we see constant speed, alarm bells should go off in our heads saying that the acceleration is equal to 0 and the net force is equal to 0. Now, if we move upward with decreasing speed, our velocity is up and our acceleration is opposite that direction, so it would be down. So that's not going to be it. If we move downward with decreasing speed, the velocity is down, and the acceleration is in the opposite direction. So that sounds good. And then downward with increasing speed is accelerating down. All right. Here's a great problem. We have three masses connected by pulleys, and we want to know the acceleration of mass 2. So, again, with this, our first look, the first thing that we do is reduce the system to one mass and one force. So, since we're looking at three objects, we've got some work to do. I'm going to go ahead and start off by sketching our forces on here. Got M1G pulling down, tension pulling up, tension pulling over. Since that's all the same string and I know I have two strings, I'm going to go ahead and call that tension 1. M2G is down, the normal force is up. Tension 2, second string, pulls to the right. Tension 3 pulls up. Now, we're going to have to make a decision, and then M3G pulls down. We're going to have to make a decision here, looking at what's going on. First off, there's no friction, so there's no more forces than that. And looking at it, mass 1 is 1.5 kilograms, mass 3 is 2.5 kilograms. That means once we release this system, it's going to accelerate in this direction. Now, the whole reducing the system to one mass and one force thing, our first big step in that is to take the acceleration and straighten it out. So when I do that, that means I'm going to have to straighten out my masses. Now, M2 is kind of already aligned to the acceleration. Got that normal force up, M2G down, tension 2 this way, tension 1 this way. We take mass 1, we want to rotate it to where here it says the acceleration's up, tension 1's up. Since tension 1 is over, since the acceleration is now over when we straighten it out, we're going to rotate it to where M1G pulls that way, tension 1 pulls this way. We got M1 in there. Same thing with M3. We're going to say tension 2 on M3 pulls opposite the acceleration, and M3G pulls with the acceleration. And then we're going to make this mass 3. Now, before we add all of our masses together, we're going to eliminate the forces that we can eliminate. Tension 1 is inside my system. It's between two objects in the system. That means it's an internal force, so we can cross it out. Same thing with tension 2. That's inside of my system. That's in between mass 2 and mass 3. And then looking at mass 2, its weight and the normal force acting on it are balanced forces. They cancel each other out, so they're gone. So now we're left with just two masses acting on our system. Two forces acting on our system. We're going to combine that into everything. M1 plus M2 plus M3. We'll have M3G pulling this way, and M1G is pulling opposite that. So if we're looking at the net force, it's going to be M3G minus M1G. So if we want the acceleration of this whole thing, it's going to be the net force over the mass. The acceleration is going to be M3G minus M1G over M1 plus M2 plus M3. Now we figured it out. All that's left for us to do is plug in our numbers. So the acceleration is going to be 2.5 times 10, so 25 newtons. That's the force M3G minus 1.5 times 10, 15 newtons, divided by 3.5 mass 3 plus 1.5 mass 1 plus 2.5 mass 2. When we do that, that leaves us with 10 newtons over 7.5 kilograms, which is 1.33 meters per second squared. That's the acceleration of the system. That's the acceleration of mass 2. Now we're not going to go all the way in solving this thing because it's just an exercise in plugging in numbers. But what I want to do while we're here, because it's good practice, is to go ahead and draw free body diagrams and do Newton's second law for each one of the masses. So we have mass 1, tension 1's pulling up, mass 1G is pulling down, and we're accelerating up. That's a free body diagram with the direction of acceleration. Direction of acceleration tells me that the tension is positive and the weight is negative. So net force equals M1A, Newton's second law. And then I got to net my forces. I got to add my forces together. So that's T1 minus M1G is equal to M1A. And at this point, if we really wanted to, we could substitute M1, we could substitute the acceleration, and we could find tension 1. For mass 2, it has tension 2 this way, tension 1 this way, normal force up, and M2G down. We said that's going to accelerate in that direction along the table, making tension 2 positive and tension 1 negative. So we could do net force equals M2A, Newton's second law for that situation. And in the direction of the acceleration, it's going to be T2 minus T1 is equal to M2 times the acceleration. At that point, we could substitute in our numbers and figure out what T2 is. Or if we wanted to look at T2 another way, we could look at mass 3. We've got 3 masses, which means we have 3 bodies, which means we have 3 free body diagrams. Tension 2 up, tension 1 down, tension 2 up, and m3g down, and my acceleration is down. So we can do Newton's second law again. Net force equals mass times acceleration. Since my acceleration is down this time and the weight is down, it's going to be positive. Tension 2 is opposite my acceleration, so tension 2 is going to be negative. Putting that together, that's m3g minus tension 2 is equal to m3a. So these three equations would be Newton's second law for this entire situation. And I could do what I wanted to with that to find any unknowns that I needed to get. All right, question 5. Two tug-of-war teams. Two tug-of-war teams are pulling on the ends of a rope. Each team pulls with 1,000 newtons. If the rope does not move, what's the tension in the rope? Now, the pitfall here is to say, okay, each team pulls with 1,000 newtons, so the tension in the rope has to be 2,000 newtons. That's kind of the gut answer that everybody wants to say with that. That's not how tension works. Tension is only as strong as it needs to be, and if we just draw a free body diagram for one guy pulling on the rope, if we look at that, if we look at Newton's third law for this, we have the team pulling on the rope, and then the reaction to that is the rope pulling on the team. Because that fits our action-reaction if A pulls on B, B pulls on A thing. Because of that, I know that they have to be the same force. So for the first person, that force has to be 1,000 newtons in order for Newton's law to be true, which means that the tension in the rope is 1,000 newtons. Now, imagine it this way. That person were pulling on the rope and the rope were attached to a wall. It'd be really easy to see that the tension in that rope is 1,000 newtons. Well, for this person, there's no difference between being attached to a wall and being attached to an unmoving team attached to that rope pulling on it. It's going to be 1,000 newtons either way. We can erase this whole thing. Doesn't matter. 1,000 newtons in that thing. It doesn't matter that there are two people pulling on it. All right, number 6. Dealing with inclined planes now. Here we want to know when the magnitude of the normal force is less than mg. And there are going to be two answers to that. We've got angles and we've got an inclined plane that we're going to deal with here. So every time we have an angle, and this is worth writing down, when we have an angle, what we need to do is break up the forces into things that are in the direction of acceleration. So if we look at the first one, that force is down. What we want to do is, instead of looking at this force, is look at the part of the force that's down and the part of the force that's over. We don't really need any numbers here. I just know that I have force in the y pushing down, force in the x pushing over. If we were likewise to look at what's going on with case 2, break it up in the same way. We have part of that force that's up, part of that force that's over. Case 3 is going to be a little trickier, and we'll come back to that. I want to look at case 1 and case 2 right now. Overall, we want to determine what the normal force on these blocks is going to be. So normal force, go ahead and finish out that free body diagram, is going to be an upward force on the block from the surface. Now in this situation, all of my forces in the y direction are balanced. So I have a force in the y that's up. Oh, I'm sorry. So upward, I've got the normal force that's up, the force in the y that's down, and the weight that's down. Now it doesn't matter really which ones I make negative, I just need to be consistent. Everything that points in the same direction should be the same sign. Everything that points in the opposite direction should be the opposite sign. So if that's the case, over here, we solve for the normal force. That's the part of the force that's in the y plus the weight. So in case 1, the normal force is greater than the weight. But that's not what we're after. So I can eliminate any answer with case 1 in it. Now, as far as test taking goes, at this point, you're done. We're selecting 2 answers. It's a little awkward, but we have case 2 and case 2 and case 3. In those cases, the normal force is less. Now, we haven't proved that yet, so let's go ahead and talk about it. Case 2, let's go. Case 2, what we want to do is finish out that free body diagram. We have the normal force that's up and the weight that's down. And for case 2, again, net force in the y direction is going to be 0. We'll do case 2 right here. Net force in the y direction is 0. Tell you what, it'll be best to do right here. And so I've got the normal force plus the force in the y direction minus the weight. Both of these forces are up and the weight is down. So I'll make those two positive, weight negative. If we solve for the normal force here, it's going to be mg minus the normal force. Great. In that case then, for case 2, the normal force is the weight minus something, so the normal force must be less than the weight. So that's one of the ones that we're going for, case 2. Case 3, we're on an inclined plane. We're on an inclined plane, we have to play by slightly different rules. On an inclined plane, objects accelerate up and down the plane. Because that's the case, because objects accelerate up and down the plane, my acceleration is going to be either up or down. When we resolve vectors, when we break them up into the x and y parts, we want them to be perpendicular and parallel to the acceleration. If we look at all the forces acting on this, you have the normal force up, I have this applied force up the plane, and I have the weight down. Weight's the force that doesn't fit. This is good to know. We must resolve weight because the normal force is perpendicular to the plane. Just as a hint, something for you to help you a little bit. Normal in this context means perpendicular. So a normal force is a force that's perpendicular. In this case, it's perpendicular to the surface. So this normal force is perpendicular to the plane, and therefore the acceleration, I don't have to resolve it, and my force here, this force F, is up the plane, so I don't have to resolve it either. So what we do have to do is break up the weight. Because we want to break up the weight, we're looking at the 2 parts of weight. So we have 2 parts of weight. We have a part into the plane. We have a part down the plane. So looking at weight right here, really zoom in so we can see it well. Part is into the plane, part is down the plane. That's part of my weight. That's the into the plane part of my weight. In this particular case, the part into the plane is going to be opposite the normal force. That's important to know when we're drawing this out. That's really all we have to do. We don't necessarily have to go into trig, figure out what's going on here. We'll talk about it after we answer this question, but it's not always necessary. So what we want to do is our free body diagram. We have the normal force and then part of the weight. So the net force in this new y direction is 0. We're not accelerating this way out of the plane. We're accelerating up or down the plane. Because of that, I've got the normal force minus part of the weight. And because we're talking about part of the weight, the normal force is equal to part of the weight. And because the normal force is part of the weight, the normal force is less than the weight because it's equal to a part of it. So, while we're on the subject of inclined planes, because a few problems are going to be like that, we do need to address the mathematical part of it. So, looking at our plane, mass m, we're going to say that this is the angle of incline of our plane. The weight of the plane, the weight of the object pulls straight down. But that's not really up the plane or down the plane or into the plane. So we have to resolve that into the part of the weight that's pulling into the plane and the part of the weight that's pulling down. So we've drawn this nice little right triangle, and we need to find out what the parts of that right triangle are. So if this angle is theta, that's 90 minus theta. That's 90, so this has to be theta. So inside of here, I just erased here. So inside of this, that angle is theta. So I want to redraw that triangle. Hopefully it makes a little bit more sense. We have mg, it's our hypotenuse. We have the part that is into the plane, and we have the part that is down to the plane. They're at right angles. Here's my angle theta. If we're going to label this as the parts of the triangle, this is my hypotenuse right here. This is my adjacent side. And this is my opposite side. And there's something that's really, really important to remember as they do this. Because you know, we're trying to find the size of a side, right? So for the adjacent side, and anytime we're talking about the adjacent side, this always has to be true. The length of the adjacent side is going to be equal to the hypotenuse times the cosine of the angle that we're talking about. So the length of the adjacent side is the hypotenuse times the cosine of the angle. So this part of the weight, mg perpendicular, is equal to the hypotenuse, mg, times the cosine of this angle. That's how I find that part of the weight. Mg cosine theta is only a part of the weight. Likewise, for the opposite side, length of the opposite side is equal to the hypotenuse times sine of theta. And again, these are rules that are good to memorize that are always true. So the length of that side, that's the parallel to the plane side, or the down the plane side. We could say mg down, that's fine. It's just what part of the weight that we're talking about is equal to mg times sine of theta. There are times when it's going to be important to be able to find this. So we'll kind of zoom out for that part of the question. We'll move on to the next one. All right, a particle of mass 1.3 kilograms is sliding down a frictionless slope inclined at 30 degrees to the horizontal. The acceleration of the particle down the slope is. All right, so we have a mass, and we want to find the acceleration. So even though we're on an inclined plane, we're still following the same steps, those steps being draw a free body diagram. So here's my plane. Here's my mass, which we know is 1.3 kilograms. And here's the angle, which is 30 degrees. And sliding down the incline, it's frictionless. So the only forces we have acting on it are the weight of the object, that's straight down, and the normal force, kind of up at an angle, because it's 90 degrees to our surface. Now looking at this, we need to talk about the parts of weight to figure out what's going on. This part of the weight is the perpendicular side. This is my angle 30, that's adjacent, so it's going to be mg cosine 30 into the plane. This is the opposite side, so it's mg sine theta down the plane. So if we were to redraw this mass and just look at the components, we'd have mg cosine 30 into the plane, mg sine 30 down the plane, the normal force perpendicular to the plane that way. And this is the plane that we have going on. Now, we have our unbalanced force in that direction. So now that we've done our free body diagram and resolved the necessary vectors, we're going to say that MA is equal to mg sine of 30 degrees. The m's cross out, so even though it's 1.3 kilograms, we're not going to use that part. And the acceleration is 10 times the sine of 30. Plugging that into your calculator, sine of 30 is 1/2. So the acceleration is going to be 5 meters per second squared. Which, I'll zoom out so we can see this again, really close to 4.9. This problem used 9.8 for gravity instead of 10. On the AP test, all the multiple choice questions will be written as if the acceleration due to gravity is 10. All right, 8, we have a select 2 answers question. 2 metal blocks of different masses slide freely down the same frictionless incline. Which of the following is true? All right, well, if we have masses on a frictionless incline, I'm okay with kind of borrowing what we did from before. Definitely the same method. Doesn't matter what the mass is. I got weight down, normal force up. Now it's good practice, it's good exercise to take and look at the components or the parts of that weight. We'll put mg right here. We have the perpendicular part of the weight and the down the plane part of the weight. That's my angle. That's my adjacent side. That's going to be mg cosine theta. This is my opposite side, so it's going to be mg sine of theta. So if we redraw that mass on the plane, normal force didn't change. We didn't really have to resolve it. But pulling down opposite the normal force, perpendicular to the plane, is mg cosine of theta. And pulling down the plane is mg sine of theta. And we're going to accelerate down the plane, so that acceleration, to continue, net force is equal to mass times acceleration. These forces balance each other out, so my only net force is mg sine of theta. That's equal to ma. M's cross out, so I've got g sine theta is equal to the acceleration. Now, if we noticed here, the mass canceled out. So what that means, when the mass cancels out, is that the acceleration is the same for all forces. Sorry, is the same for all masses. So regardless of the fact that these two different massed blocks slide down the plane freely, they both will have the same acceleration. Their acceleration down the plane does not depend on their individual mass, just on the angle of the plane. So if they have equal accelerations, can't have unequal accelerations. If they have equal accelerations, they should reach the bottom at the same time if they're released at the same time. So it doesn't matter least massive or more massive. Then we have this last one. This says they have equal accelerations. That's true, but the forces acting on them are unequal. That is absolutely true. So if we look at that, the weight depends on the mass. The object with the bigger mass is going to have more weight. That means they have unequal forces acting on them. For this multi-select, A and E are both true. All right, let's move on to number 9. All right. Hey, we have a block sliding down a frictionless inclined plane. We've done this more than once now. So we're asking for the free body diagram, and it's a separate alone free body diagram. So this goes for you looking at free body diagrams, and this goes for you drawing free body diagrams. But do not put components. Sorry, I didn't spell that right. Do not put components on official free body diagrams. You only resolve forces on your working free body diagram. If the College Board asks you to draw a free body diagram, it really doesn't want to see components at all. Doing that will invalidate your free body diagram. Also, when you're given a free body diagram, it will not have components on it. We will not be breaking gravity up in this situation. So if we're looking at an official free body diagram, all that matters are the whole forces. So let's look at the whole forces representing this block sliding down a frictionless inclined plane. I know that weight is going to pull straight down on the object, and I know that the normal force is going to push perpendicularly to the plane. Since it's frictionless, those are the only two forces acting on it. There are just two forces. So 5 is the only one that shows two forces. The rest of them show part of the components of the weight, but not really all of the parts of the component of the weight. None of the rest of them are right. None of the rest of them represent just the two forces acting on our object. Okay. Number 10. 2 kilogram block rests on an inclined plane, and we want to know the frictional force between the block and the plane. It's at rest on the inclined plane. This doesn't need to have the same kind of bells and whistles for you that having constant velocity does, but rest is important. Rest means the velocity is 0 and not changing, and the acceleration 0, and the net force is 0. Be good to know that. So before we do the rest of it, we should do a free body diagram to figure out what's going on. And this is just a sketch. So we have the weight pulling down and the normal force pushing out at an angle. And since there's a frictional force, we're going to have friction up in that direction. We want to know how much that frictional force is. Well, in order to do this problem, we need to take the weight and break it down into the part that's perpendicular to the plane and the part that's parallel. The part that's pulling into the plane, the part that's pulling down. That's going to be my angle theta. That makes the pulling into the plane part the adjacent side of my triangle. And so the length is going to be the hypotenuse times the cosine of that angle. And this part down here is the opposite side. So it's going to be the hypotenuse or the weight times the sine of the angle. So we can take that mass and redraw the free body diagram. We have mg cosine theta pulling into the plane. Mg sine theta pulling down the plane. Normal force pulling perpendicular to the plane. And friction pulling back. Now we know these two balance because we're not jumping off of the plane or crumbling down into it. And we know that these two balance because we said that the net force on this entire system is 0. So if we wanted to be formal about it, we could put it into Newton's second law for this situation. Net force equals mass times acceleration. The net force is going to be one of the forces, mg sine theta, minus the other force, going to be equal to 0. So that tells me that mg sine of theta is equal to the friction. Well, we know that theta is 30 degrees, and we know the mass and the weight, so 2 times 10 times the sine of 30 degrees is equal to the force. So 20 times 1/2 is equal to the force, and that makes the force 10 newtons. Again, what's really important about this is that we're talking about parts of the weight, not all of the weight. All right, so we've got some free response. Another good opportunity to pause and look at the free response before we get going. All right, this is a common thing that happens. This is like a qualitative quantitative problem. You are asked to break down the problem two different ways, one with numbers, one without numbers, so that you can explain what's going on in multiple different ways. And often on those problems, you will be given two student statements and asked to evaluate the correctness of those statements. So let's look at this problem. We have two blocks, M1 and M2, connected by a light string that passes over a frictionless pulley, and these things are initially at rest. There's friction between the incline and mass 1, and two students make the following observations or predictions. Ruby says, if we reduce the angle of the incline, the normal force on the block will increase, causing the friction on mass 1 to also increase, but mass 2 will pull harder on mass 1, and the system will accelerate in the direction of mass 2. Levi says, increasing the angle of the incline will cause the part of gravity that pulls the block down the plane to increase and the normal force to decrease, reducing the friction and causing the system to accelerate in the direction of mass A, or mass 2. We want to know what part of Ruby's statements are incorrect, what part of Levi's statements are incorrect, what parts are correct, and then should the angle of incline be increased or decreased in order to make the system accelerate in the direction of mass 2? Justify your answer. So with these qualitative quantitative questions, they come in this order. What's right, what's wrong, you answer the question now. My advice for this is always to jump into the you answer the question now part. Then you can go back and deal with the student statements after you have already decided what's right and what's wrong, instead of you trying to figure out the problem at the same time that you're trying to evaluate these student statements. So the best thing for us to do then is to start with solving the problem. Start with solving the problem. And that's down here in part E, not even breaking apart their statements yet. So we're not even going to deal with that. So to break down this problem, we have two masses tied together and there's friction. Let's draw all our forces. M1, M2. And then let's straighten it out. Let's see kind of how this system behaves. We have M2G pulling straight down, tension pulling up. Same string, same tension. Tension's pulling up the plane. I've got a normal force. I've got a frictional force because they tell me there's friction. And I have M1G pulling down this way. Now looking at it, M1G is not really in the same direction as everything else. It's not up the plane or down the plane. So what we want to do is break that down. Before we go anywhere else, we'll look at these two parts. We got theta right here. We have the part of the weight that's pulling down into the plane, and we have part of the weight that's pulling down the plane with friction. So we'll call this part, because it's adjacent to our angle, mg cosine of theta. And this part that's opposite my angle, mg sine of theta. Now it's pretty hard to see it, so I'm going to erase the weight. And I'm going to redraw mg sine theta right here. I'm just gonna take this and move it up and stick it on my mass. That way I can see what it actually does to the mass. Put it a little bit closer to that. Now, if we accelerate, it's going to be in that curved direction. That's not too helpful for me. So I want to straighten my system out along this line. So let's look at mass 1 and all the forces acting on him. We got the normal force. I have that up now. And opposite the normal force, we had mg cosine theta. And pulling this way was mg sine theta. And friction that is attached by a string. So there's tension pulling this way. Tension pulling in the opposite direction. The mass 2. And we said M2G was pulling opposite that tension. So, let's say for now, we want to accelerate in the direction of mass 2. So we're gonna go that way. It's gonna help me look at my forces a little bit better. Let's look at all these forces and eliminate what we can eliminate right now. Okay, tension is an internal force, so I know that it goes away. The mg cosine theta and the normal force balance each other out. So they go away. That's great. So now I can put those two together. We've got M1 plus M2. We've got M2G pulling this way. And M1G sine theta pulling this way. Friction pulling that way. If I want to look at my acceleration in that direction of motion that we want towards mass 2, going to be M2G minus M1G sine theta minus friction divided by M1 plus M2. But I have a friction problem here. I don't know what that is. Friction in general is mu times the normal force, so it's going to be mu. And since I said the normal force balanced with mg cosine theta, mu m1g cosine of theta. Now we're going to have this rather gruesome expression for acceleration. Acceleration is m2g minus m1g sine of theta minus mu m1g cosine of theta, all divided by m1 plus m2. So, I want to analyze that statement just a little bit so we know what's going on. This that is the pull of mass 2. And the pull of mass 2 doesn't ever change. It just depends on that mass, and if I adjust the angle, that doesn't go anywhere. And then we have m1g sine of theta. This is the part that pulls down the plane. Okay, so as the angle increases, m1g sine theta increases. So that pulls harder against mass 2 as the angle goes up. And then we have this frictional term, mu, which is in general a small number, and m1g cosine theta. This is the part that pulls into the plane. So the part that pulls into the plane is cosine theta. We look at that specifically, since it's pulling into the plane, as we increase the angle, less and less and less of the weight pulls into the plane. So as theta increases, this part gets smaller. But it's multiplied by a small number. So if I increase the angle, m1g sine theta goes up, m1g cosine theta goes down. But again, because we're multiplying by that smaller number, the bigger m1g sine theta gets, the more it pulls against m2g. So if I want this thing to accelerate towards m2g, I want the angle to go down. Then m1g sine theta doesn't pull against me as hard. And that's even though m1g cosine theta is going to get bigger, but it's multiplied by mu, so it's not as important as what's going on. Let's put that into words to answer our question, and we'll refer back to this. And we'll refer back to this often, especially as we're going and looking at what Ruby and Levi are saying. So we'll kind of write the whole thing down here. The angle of the incline should be decreased. A decreased angle reduces the part of weight that pulls opposite m2g. So we have more net force in the direction of m2g. Oops, sorry, I got ahead of myself. Decreasing theta increases the normal force because it increases the part of weight that's pulling into the plane. And it increases friction. But because, mu is a smaller number, this is a smaller effect than what happens up here. That's why we should decrease the angle. So let's go back through and look at Ruby and Levi's statements and pick out what's true and what's false. We'll look at Ruby first. So Ruby says, if we reduce the angle of the incline, the normal force on the block will increase. Is that true? Absolutely. So let's highlight that with yellow. The normal force on the block will increase, causing the friction on mass 1 to also increase. That is true. But mass 2 will pull harder on mass 1, and the system will accelerate in the direction of mass 2. Let's pump the brakes here. Mass 2 cannot pull harder on mass 1. So that's false. Let's talk about Ruby's statements and talk about why parts of them are incorrect. The incorrect part, and for this, your best bet is to quote exactly what's said, right? So you don't have to do a sentence like, Ruby's statement is incorrect when she says that. You don't have time for that. Just put in quotations, mass 2 pulls harder on mass 1. The weight of mass 2 constant, and because mass 2 is hanging, it doesn't depend on the angle. That's why that statement's wrong. She's wrong in saying that. Now, since we've already broken apart her statement, and we're allowed to skip around on parts of this question all we want, let's talk about the things that she gets right. She is correct in saying normal force increases and she's correct in saying that because of that, in as much as you possibly can, please quote the parts of the question that are correct or the statements that are correct and incorrect. And it can be a very brief explanation, but please, please, please be very clear on what you're choosing there. Now, the normal force increasing as we reduce the angle of incline. The normal force depends on the part of the weight that's opposite or that pulls down into the plane. From our little diagram here, we can see that normal force depends on the mg cosine theta part. And as I reduce the angle of the plane, more of the weight is in the same direction as the normal force, increasing the normal force. Let's write that down. As theta decreases, more of the weight is in the direction of the normal force, increasing the normal force. And as the normal force increases, so does friction, because we know that friction is directly proportional to the normal force. All right, that's breaking down Ruby's statement. That's much, much easier to do once we've already answered the question. Go ahead and break up Levi's statement as well. We'll do the same thing. We'll highlight all the correct parts in yellow and the incorrect parts in blue. So, Levi, increasing the angle of incline will cause the part of gravity that pulls the block down the plane to increase and the normal force to decrease. So, part of gravity that pulls down the plane will increase. That's true. And the normal force will decrease. That's true as well. Reducing friction. That's true. and causing the system to accelerate in the direction of mass. That part is not true. So let's jump in and tackle Levi's statement. First thing we want to talk about is what part of Levi's statements is incorrect. He's incorrect in saying increasing the angle will cause acceleration up the plane towards mass 2. You want to say it that way. That's not going to happen because what Levi is doing here is ignoring the part of gravity pulling it down the plane. So we know that as theta increases, the part of weight pulling down the plane gets bigger and pulls the system down the plane. That ultimately beats out friction getting reduced because that's a bigger effect. And then what part of Levi's statement are correct? That's the angle stuff, right? So as theta increases, the normal force decreases. Friction decreases. And mg sine theta increases. We saw how all that worked down here. So again, on this qualitative quantitative thing, please take the time to answer the question first before you start analyzing statements. To put it in kind of educationalese language, evaluating statements is cognitively much harder to do than solving problems. So solving the problem first gives you some handholds, gives you some scaffolding to break apart those statements and figure out what's right and wrong. All right, that's our session. Thanks for listening in.